Hello. Hello. Good evening to all of you. Let's start the meeting. Here we will discuss the third assignment, and for today's session, this is the first question. Please read. The electron drift current in. So this is the first question. What is question? The electron drift current in a semiconductor is due to drift current. So two type of current is generally in the semiconductor. First is diffusion, second is drift. So when will be drift or when will diffusion? Let's discuss one by one. If the concentration gradient is there, then is diffusion. Let's say electron, 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 too much electron this side, and this side is so electron generally diffuse from n side to p side due to concentration gradient. Which is known as, if the electron is moving one place to another place, is generate current and known as diffusion current. On the other hand, drift current is basically driven by electric field. Let's say here is electric field, let's say is minus, there is plus, 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 minus, minus, minus. Direction of electric field, what is the direction of electric field here? That side, positive to negative. Yes, if let's say here is an electron, do you know which force is applied here? Coulombic force, you know. So if the direction of electric field, let's say x-axis, let's say this side is x-axis, so what is the force direction? Let's say electron is E, charge of electronic, and let's say is, so what is the direction of force here? Let's put in this way, the opposite of the electric field, so electron move this side. Okay, if this phenomena is known as drift of electron, and due to this drift, current is generated. This current is known as drift current. Okay, so please answer now. Which one is correct? You can write answer in chat box. Yes, please. So here we anyone please answer. Electron drift current in semiconductor due to first an electric field, B both carrier concentration gradient and electric field, third is defects, fourth is carrier concentration gradient. Which one is correct for this? Simple, you can see here electric current due to electric field, electron is drift due to Coulombic force. Yes, so this phenomena in semiconductor is called as drift current, which is due to electric field, and this phenomena happen at the PN junction. Electric field is generated inside the PN junction in the depletion layer. Okay, any doubt? Let me if I have electric field like that, this is positive, 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 negative, negative, negative. Let's say you have an electron, or let me put the one electron somewhere. So electron is, if the so many particle or electron is there, so motion will be zigzag like that of electron, maybe some like that. So this electron is feel Coulombic force. Due to Coulombic force, electron can move from this side to this side. This is the direction of electron. If the electric field like that, okay, and this electron is drift to electric field. So answer A is correct. Let's move for second question. At which position in the band gap do the shallow trap level reside in p-type semiconductor? Yes, please answer this question. Or let me also ask for Fermi level. Let me discuss this question. Sorry. If we have semiconductor material, so you know conduction valence band and conduction band. Yes. So this is like that. We have a minima of the valence band, sorry, conduction band, maxima of the valence band. This is ek. This is sorry k. This will be so which position of the band gap do the shallow trap levels reside in p-type semiconductor? Let me discuss with first is intrinsic semiconductor is Fermi level is like that for intrinsic semiconductor. If let me if be n type, if be p type, then tell me where will be the Fermi level closer to the valence band. This is Fermi level for p type, Fermi level for n type. Yes, clear? So you know in p type shallow trap, where will be the shallow trap? In p type semiconductor should be near like that trap. Okay, this will be shallow trap for p type and near like that here will be shallow trap for n type. Now please answer this question. Sorry. 1 minute. Yes, please. You can write you can give me answer in right chat box. Please choose a correct option and answer your question to in right chat box. If you understand or not, then please ask. Yes, please. So cello trap, where will be the cello trap in P type? Please see this picture. Let me highlight it. Please see this. So you can see the cello trap near the, this is V valence band. What is this? This is valence band. This is conduction band. H. So answer V, just above the valence band for P type. Okay. A question or Fermi level you can see also near the valence band for P type. If question asks like that, N type, then what will be the answer? Near conduction band. For N type, but for P type, near valence band. Okay, clear? If you have doubt, please ask. Next question. Yes, please. Please see the question. What is the change in the electron energy value of wave vector k if wave vector k change from k to 4k? When the electron is in free space. So do you know the relation E versus K? We have discussed in last class. Parabolic. Yes. So let me tell you relation. This is the relation E and K. Now read the question. If the wave vector change from K to, let's say for K, energy is, and for K, energy is, let's say E2. This is same, but in this case, put 4K. Now calculate change in energy. Delta E means E2 minus E1. 16h square K, and this. So change in energy will be 15h cut square K square by 2m. Clear? Any doubt? So let's discuss next question. Forbidden energy gap of silicon material measure on EK diagram is difference between forbidden energy gap in EK diagram. Please read these options and try to choose the right option. Then I will discuss. But first try to yourself think about this question. So what is forbidden energy gap? Let me tell you. If I have material like that, which is, this is K, this corresponding A. This is valence band. This is conduction band. Or let me discuss in 1 minute. I have this is valence band, this is conduction band, material like that. Or maybe put in another way. 1 minute. So do you know where is the global maxima or minima for this function? Because minima first here, second here, third like that. Let me put also 4 here and maxima in the valence band 1, 2, 3 like that. So we have to find this gap is known. Let me put this gap is known as forbidden energy gap, or we can say in the other term band gap of material. Also, this is known as forbidden energy gap, or known as also material band gap. Easy. So the forbidden energy gap silicon material in EK diagram is the difference between we have to choose minima in the conduction band, not minima, global minima. So lowest part of, let's say if this is above, but this is lowest, and maxima, topmost maxima, let's say here. For this function here. So this gap is known as easy for this material. So which option is correct? Global minima of the conduction band and global maxima in the valence band. Clear? We have also picture for you. Reference. Let's say this is direct, this is indirect band gap, but let's say this is for silicon. We have minima 1, 2, but minima of 2 is below as compared to 1. So we have to find global minimum. This is global minimum for this curve and global maximum of the valence band. This is maximum. So this gap is known as forbidden energy gap or material of the semiconductor. Okay, clear. Let me ask one question. I have curve like that. So where is the global minimum for this? One, two, or three? Where? E3, E2, E1. Where is the global minimum for this curve? Conduction, band edge. This is one valence band maxima. This is also maxima. This is also maxima. But we have to find the global topmost maxima and topmost minimum. So this is third number. This is the global minimum, and this is the global maximum, and this is the forbidden energy band gap of material. Clear? So let's move on. Next question. Which of the following is the reason for band bending observed in a semiconductor material, and the position of the band bending? Option A, presence of the electric field at the interface. Absence of the electric field at bottom. No concentration gradient. Concentration gradient. So which option is correct? Why is band bending is happening? Let me discuss. I have p-type material. I have another n-type material. If I want to combine both the first and second, then what will happen? For p-type, this is the Fermi level. For n-type, this is the Fermi level. This is valence band, conduction, valence and conduction. Okay, if I want to join these two material, these two semiconductor, bringing together, then what will happen at the equilibrium condition? What will happen? Please think. So let's say this is P, this is N. So scenario like that. At equilibrium condition, one Fermi level, only one Fermi level is present in the material at equilibrium condition. So at the interface, band bending is happening, and this is due to the presence of the electric field. This is depletion region, and air is the, let's say this side is electron is goes out, positive, 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 and negative this side. Immobile charge time. So electric field is generated air. So clear? Answer will be presence of the electric field and position at the interface. Any doubt? So let's move. Or another way we can see the potential difference, which is also give the electric field. Next question. Which of the following parameter can be determined from the whole measurement? And also which is cannot? Please think for this question. So whole measurement we can determine charge carrier density, charge carrier type, and charge carrier diffusion length also, but we cannot determine charge carrier lifetime and charge carrier movability. Charge carrier lifetime we can measure from the TRP, time resolved photoluminescence. Okay, and movability, how we can find the movability? Which measurement can give movability? Please think and give me the answer in next class. Please search. Next question. Which of the following represent the dependence of the charge density on the electric field in the depletion region? Do you know depletion? Where is the depletion region? Let's say we have n-type, p-type material. Here will be the depletion region, and band bending is also in this region. So, what is the question? Charge density. Let's say rho for 2D, 3D, for 1D, lambda, 2D sigma, and for 3D, charge density is symbol used for charge density. These are the, this is linear, this is areal, this is volume 4. Okay. So this is formula. Charge density is directly proportional to change in electric field with the distance. Okay. Do you know electric field? Let's say I have a Q charge and force of is E. F, sorry. This is the Coulombic force on charge Q. Field electric field is if the test charge is Q. This is the formula for electric field. Charge density, how can we correlate? Total charge, let's say Q charge is present this volume V. Charge per unit volume is known as charge density. So in this way you can correlate density from the charge. Let's say this unit volume delta V is the charge density. Charge is delta Q. Charge density will be same everywhere. So dq by on this length, sorry, a minute. Let's say this is dv volume, rho into dq. If I want to find out the total charge, we have to integrate. So you can put here rho charge density F and dq. So here you can also find out the proportionality sign. E is directly proportional to the charge density, electric field. Okay. Next question. When an electric field of intensity 12 volt per centimeter is applied across the semiconductor at a certain temperature, the average drift velocity of an electron is 60 meter per second. The electron mobility in the semiconductor is, these are the 5 options, sorry. Answer is G, but please find out, you can use this formula. You can take 5 minutes for this question. Please solve this question. Electric field intensity is 12 volt per centimeter. Per cm, and average drift velocity for electron is Vt 60 meter per second. So you have to find the movability. You can use this relation. This is simple relation. Please find out, you have the value, and check this is right or wrong. Option E is correct answer or wrong. You can take 5 minutes for this question. Please solve. Please try to everybody. So put this value in this equation. question first. Let's say VD is 12 volt per centimeter. Please convert into SI unit. 1 semi equal to so 12 volt per centimeter equal to mu. What is mu? We have to find mu and E. Sorry. 1 minute. So VD is 60 meter per cent. We have to find mu and E is also, but here is meter per second, so you have to convert meter into centimeter. Let's convert. 1 meter equal to 100 centimeter. So this is in 10 to the power 2. I have converted here 1 centimeter equal 10 to the power 100 centimeter, and this is also, so movability mu will be 60 10 to the power 2 centimeter per second divided by 12 volt per centimeter will be centimeter square volt per second. So is the right answer. Clear? Next question. Semiconductor material for good solar cell. I want to make good solar cell as much as. So which type of recombination will be happen? Should be happen? Or which type of recombination will be necessary? If I want to make as much as good solar cell. So which type of recombination should be there? We know if the defects in the solar cell, let's say this is material I want to use in solar cell, but the defects is there which leads to loss of what? Loss of photon, which is due to the defects. So efficiency leads to reduce in efficiency. Okay, so if I want to make good solar cell, so our material should be defects free. Okay, so defects can be shallow trap or trap RG center can be happen, but if the material which is purely defects free, then let's say this is hole, this is electron, or This is electron, this is hole, electron, 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 and hole. If they can relax, recombine electron to hole. This is valence band and conduction band. Via band-to-band recombination, non-radiative recombination, then H nu photon is emission. If we measure the PL, gives sharp edge like that. So if you want to study the defects, you have to measure PL. This side intensity, this side is wavelength. So you will get sharp peak at the near the band gap. At the band gap, let's say this is 5.2 electron volt, and this is also the band gap of 1.5. If trap is there, let's say this is shallow trap. So our photon, or if we recombine in this way, so let's say we receive this that much energy via photon h nu, but we use that much only in the process where we generate the electron hole pair. So this energy goes to defect. Due to the defects, material can relax via heating or phonon generated. So defects leads to what is material can heat up. This is goes to energy our considered photon is heating or phonon. So you have to make defects free. So band to band recombination should be there, will be happen if your material is good. If defect is there, then electron and hole recombine via the shallow trap or trapped RG center. In between is RG center. This is corresponding to the shallow. Okay, clear? Let's move for next question. Yes, please answer. This is the question. Which of the following statement is true? Yeah, let's read. Direct bandgap material has larger absorption coefficient, and absorption in direct bandgap semiconductor involve only photon. Absorption in direct bandgap involve only photon absorption or emission. Indirect air material exhibit lower absorption coefficient as compared to the direct bandgap semiconductor. So let me discuss first the direct indirect. One minute. Are you listening me? this is sorry, K, this is E in this direction. So this material is indirect and this is direct. Why? Indirect material band gap only energy exchange, but photon wave vector will be zero, but here both are non-zero, not equal to zero. Here is energy also change, material electron and hole recombine by like that. So that much is K changes, so this is not equal to zero. Also E is also changes. This is also not equal to zero. Indirect band gap delta K or wave vector K momentum should be zero, but in this case indirect momentum will change also. So now please answer up then question. Yeah, absorption also direct band gap material has larger absorption coefficient. This is right. Absorption in direct band gap semiconductor involve only photon. What is this? This is right or wrong? You can see absorption in direct band gap semiconductor involve only photons. Yeah, there is no phonon. There is phonon, but there is no phonon. So this is also right. Absorption in indirect band gap involve only phonon absorption or emission. So this is right or wrong? Please think. You can see the picture. Indirect band gap material exhibit lower absorption coefficient as compared to the direct band gap semiconductor. Yes, this is right. If phonon is there, always loss of our incident light. We cannot convert it 100% to the electron hole pair. So if phonon phenomena is there, then absorption coefficient always less. Okay, so absorption in indirect band gap involve only phonon absorption or emission, not phonon, photon, change of energy, all are there. So this is wrong. So A, B and D are correct option. This is wrong option, false statement. C is false. Clear? Next question. Yeah, you can see the absorption coefficient alpha H nu in direct band gap semiconductor is given by. So option A is correct. This is formula. B is the constant. V by H nu in bracket H nu minus Eg to the power 3 by 2. So use this equation. Let calculate the absorption coefficient alpha H nu in direct band gap semiconductor. The photon has energy. You have energy 1.6 eV and 1 LV. A and B, there are two. There is two part. There are two part here, and the band gap of the material is 1.4 eV. For alpha A part, please solve this equation. If you have material band gap 1.4 eV, this is valence, this is conduction. Let's say if you have photon, let's say energy 1 eV, h nu equal to, can this photon is absorbed this by this material? Yes or no? You cannot excite the electron from air to air. So this, because energy is less than the band gap of the material, so B is 0. There is no absorption. This is transparent too. This photon is transparent too for this material. So this is 0. But for first part, you have to calculate, let's say h nu energy is, what is energy of the photon? 1.6 minus Eg 1.4 to the power 3 by 2. This is constant. This is 0.2 to the power 3 by 2. Please solve this equation. You can find out the answer. Okay. So this type question may be asked in exam. 11, 11A. This is B. Clear? Next question. Which of the following simplification is used under steady state condition in p-type semiconductor? A P and R the carrier concentration under the arbitrary condition. This is delta NP, and delta Pn are the deviation in the carrier concentration from their equilibrium values. This is change in electrons concentration in p-type semiconductor. P-type, that's why P is used here. This is in n-type. So answer is B. Under steady state condition, change in delta concentration of electrons or perturbed electron over the infinite time or steady state goes to 0. Okay. If question asks like that, n-type 4, this is for p-type, but question may be asked for n-type also. So delta change in will be or the or 0 when equilibrium or t tends to infinite. Clear? Next question, which when there are multiple recombination mechanism present, how one can determine the effective minority carrier lifetime for the all process combination combined? Option are, these are the option. If you know the answer, please write in chat box. Yes, please. So, answer is C, but let's discuss. We know the process, generation and recombination. Band-to-band generation, RG center. This is midway. Im- impact ionization. Recombination, band-to-band, RG, cello, excitons, or OJ. But let's see. Direct band gap semiconductor recombination is mainly band-to-band. So this is useful material for solar cell. But in direct material game, material like that, recombination is mainly RG center, non-additive, multiple recombination can happen, and which is can be given by recombination is band to band, RG center, exciton, OJ or cello. So recombination is inversely proportional to the lifetime of charge carrier, or we can use proportionality in A. So this is the process. If we multiple recombination is happen, total recombination we can use like that. RSH, OZ, all are these we can combine here. So put this value here, you can find out the relation for multiple recombination mechanism if present in the material. So effective lifetime can be given as okay. Next question, the relation between the majority carrier lifetime and carrier diffusion length in p-type semiconductor is. Yes, please. This is the formula, but we will discuss the question here. Calculate the diffusion coefficient of electron. You have to calculate D at 300 Kelvin in a n-type silicon doped with the movability of electron. You have to given here movability and the this is the S atoms per centimeter cube doping with silicon. So this is the ND doping 10 to the power 15 atom per centimeter. So please solve this equation. So 1 minute. Do you know this equation? This is known as Einstein relation. KT by E equal to D by, and at 300 Kelvin KT value will be 0.0258 electron volt, and U is electronic charge. So please put this value in this equation and find out the D. Okay, please you can see the solution, but I'm asking another question. You have to find out the diffusion length here if lifetime of charge carrier is around, let's say, 10 microsecond. Minus 6 second. Please find out the diffusion length for this question. You have D. You can use D from here, and you have tau. So you can take 5 minutes for this calculation. Please understand the calculation if you and solve this question. Okay, please take 5 minutes and solve. So answer please. Did you get the answer? Yes or no? So this is the simple equation you can use if you have diffusion centimeter per second and 10 to the power minus 6, or you can use minus 5. So what is this value? So we can use in simple way 3.354 into 10 to the power minus 4 square root, which is square root of 3.354, which is around 1.83 10 to the power minus 2 centimeter, or around 18.3 what is millimeter. This is a hypothetical question. Diffusion length okay, so this type of question may be asked, so be ready for this type of question. Okay, so here is the derivation of Einstein relation. You can see, or you can check, if the velocity of the charge carrier is v, lifetime is t, so this is length, can travel. We know the velocity equal distance upon time. So this is this relation, and we know the energy, kinetic energy kT by 2 equal to half mv square. Use this, and if you know the relation Einstein relation, use this relation in this, you can easily find out the diffusion length, which is related to L equal to under root of diffusion coefficient and lifetime. Okay, next question. Shallow trap level in N-type semiconductor reside at which position within the band gap? We have already discussed this question. Please now answer. Yes, N-type semiconductor, you know N-type. This is conduction, sorry, this is valence. This is conduction band. Fermi level closer to the, for N-type, to the conduction band. Shallow trap will be there. Okay, so which is the right option? Just below the conduction band. Sorry, valence band not. This is conduction band. Okay. Next question. You can see also. Sorry. if this is p-type, but this is mechanism is a, you can see this is for shallow level, these ed, this is n-type for n-type, and this is for p-type level of shallow tracks. Okay, next question. Where do RG center lie within the band gap of n-type? RG center always lie closer to the mid gap. Okay, material is n-type or p-type. Okay, you can use this reference or you can read. If you have doubt, you can ask me. Okay, next question. The electric resistivity of n-type semiconductor, this is rho resistivity 10 to the power minus 3 ohm per centimeter, hole movability and electron and hole movability mu h and mu n. Electron for 900, for hole 550. Unit is centimeter per volt per second. The donor concentration would be, you have to find ND. Please find yes please, these are the options. Solve and find the right option. Sorry. So let me discuss. Answer is A, but let me tell you the, you know, conductivity N E mu or donor acceptor you can use. Okay, so 1 upon rho, this is relation. So rho 1 upon nd mu of electronic charge. Please use this equation and try to solve. If this material is n-type, so concentration of electron is too high, so you can use nd only. We have to use number of charge carriers, electron E mu E, and number of holes, electronic charge, and mu h. But material is n-type, so n is too high as compared to number of holes, so you can use only this relation mu of E or n, sorry, small n equal to nd in this equation. So finally this equation. Now put the value. Rho is given, probability of electron also given, electronic charge 9 coulomb. Please put these all value in this equation and find out the ND. You can take 2 minutes. Please tell me the answer. You have to use this equation, rho 5 into 10 to the power minus 3 and J, probability of electron. What is 900? This is also in some minute. And electronic charge 1.6 into 10 to the power minus 19. So NT will be 1.6 into 5 into 900 into minus 90. Yes, you can solve now this equation. This will be plus 19 sorry, you have to find in per centimeter cube. Please solve and tell me the answer. Let me show you to the solution. This is the relation. Yes, and this is, we have also same, get the same, and here any doubt in this process, if you let me know. Let me ask in another way. This is, let's say, p type. Okay, all are the values are given. Now please find out yourself what is the, sorry, and acceptor density. Okay, this is for to you. You can solve like that. Nothing is changed. You have to just accept the electronic charge and movability of hole. Please use this equation for sorry. But if material is semiconductor is intrinsic, then you have to use concentration, doping concentration, or let's say then you cannot use single lesion. You have to involve all rho E can mu H and mu E for donor and for acceptor also. If material is intrinsic, okay, or pure semiconductor. Any doubt? Guys, are you there? So, this is the last question of today session. The absorption of a photon of energy EPH is in a semiconductor material with band gap Eg take place only when. This is simple question. Please answer. I'm requesting to all member, all attendee, please choose the right option. Let's say this is material band gap is Ag. Incident photon energy is EPH. Electron and hole. Electron can jump from here to here only when energy of photon is less or high or equal to. Please choose and think. Let's say high or equal to or less than, which is correct option C. Okay, so if this electron receive H band gap receive energy H match the band gap, then only jump from here to here. So this is the criteria, at least equal to. If higher, then easily can jump from here to here. So C, yes, C is the right option. Thanks for your. So this is the process. Electron can jump from conduction valence band to conduction band only when the energy is higher or at least equal to the band gap of the material. This is not, this is gas. Okay, so this is all about for today's session. Thanks for your kind attention. If you have any doubt, you can ask. Guys, if you have any doubt, you can ask me. Okay, let me come to the whole way we discussed. Yeah, whole measurement in laboratory we have performed. We have a semiconductor like that. Let's say we have material. Okay, if we apply external source, battery, and electric field also the magnetic field, let's say B, and let's say electron. So electron can feel two type of force due to, first is due to electric field, and second is due to magnetic field. So here we measure the whole voltage in this process, and use this equation we can calculate. If we use n-type material or p-type, the polarity of the material we can determine easily. The direction of the electron or holes can easily determine by these fields. Okay, so type of material we can easily determine. Also we can determine the density, charge carrier density, from the expression of hole measurement. And also you can calculate if you own diffusion length, how much electron is travel. So you can check in any book and read the process. If you don't understand, you can ask me in next lecture. Please first read yourself and check how electric field is, which direction is magnetic field, and how the force electron is feel generated electron. Okay, so here we can find out this type of material. N type or P type. Okay, because electron or hole has a different direction via these two electric field and magnetic field. Okay, and we can also calculate the charge density. If you calculate the hole voltage, we can use this relation. If you know this relation, you can easily calculate, and as well as also the diffusion length. One minute. Sorry. Let me tell you the expression also. Here is discussion. Yeah. Can I discuss in detail? One minute. Take this. Sorry, my this. Hmm. So force concept is here. Force is due to electric field and magnetic fields can be use this equation easily calculate direction of the applied force on the electron and majority carrier electron can be calculated from here to N type or P type resistance of the hole from the voltage V. This is magnetic field direction formula. So you have to use 2 to 3 formulas in this equation. You can find out by yourself and check this is right or wrong and how we can find. Okay, so this is the basic of the physics. in the whole measurement. This is Lorentzian force due to magnetic field also as well as electric field. Okay, so this is based on simple 12th physics. The experiment you can calculate. Why this is in is stuck. Okay, similarly whole whole measurement for probe method, for probe method is also for we have we have measured the voltage in these two inside and flow the current outside. This is give resistivity. 2 pi s v by I, like that equation. So we can also calculate the resistivity from here. So these are the simple experiments you can find out in any book. Please read. If you don't understand, please let me ask in next lecture, okay? But please understand by yourself first. If you're not able, then let me know. I will discuss in next class in detail because it will take around 30 minutes. Okay, so thanks for your attention and asking the question. Any else? Okay, thanks to all of you. We will meet in next Monday, upcoming Monday. Okay, so okay, thanks for that. Let me close the meeting. Okay.